Lithium batteries. You might not see them, but they're all around you, hiding in plain sight. Heck, chances even are you've got one in your hands right now. And you didn't even realize it. Wait, how does he know that? But how safe are they? Like, how likely is it that something like this will happen to you? And do you know what to do if one of the batteries around you right now would fail? Because it might not be as easy as simply throwing it in a bucket of water. In this video, we'll ignore all safety warnings and take them to the extreme to uncover the dangers that hide within them. So you know exactly what to expect and what to do in case it ever happens to you. We already found out exactly why batteries come with such a long list of safety warnings in the last video. And looking at the more than 7,000 comments, that video really struck a nerve by many people. And also answered a lot of yet unanswered questions you guys had about batteries. But it also raised a lot of new questions, like, are full batteries more dangerous than empty ones, for example? Or how can you stop or how do you extinguish a battery fire? And should electric car drivers be worried? Because yeah, they're sitting on top of not just one, but several thousands of these. To answer those and many other questions you might have, we're going to do 4 new experiments today. For each of which I built a new test trick. And just like last time, I made them remotely controlled so I can trigger them from a safe distance. Let's start with by far the most common question you guys had. Are fully charged batteries really more dangerous than empty ones? Well, let's find out. I've got 2 identical lithium-ion cells with one slight difference. This one is fully charged all the way up to 100%. And the other one is discharged all the way down to 0%. And to make sure both batteries are going to fail in exactly the same way, I made this guillotine style test trick, which is loaded up with a sharp steel nail with a heavy steel weight on top that's lifted into position and locked in place with a little RC servo. So as soon as I flip this switch, the weight drops and slams the nail deep into the battery, hopefully puncturing enough layers to start thermal runaway. So, time to find out if fully charged batteries are really more dangerous than empty ones. Let's start with a fully charged battery. Ready? In 3, 2, 1. Okay, so puncturing a fully charged battery means instant ignition, followed by an intensely hot and flaming jet of plasma that reaches temperatures far beyond 420 degrees. So an immediate reaction. But that doesn't answer the question yet, because your question was, will puncturing a completely discharged and empty battery fail in the exact same way or not? So, let's find out. With a new nail, same drop height, same impact. But this time, instead of the fully charged battery, the empty battery. Here we go in 3, 2, 1. Well, definitely not the same. Based on these results, the amount of stored energy clearly influences how violent a failure becomes, turns out. However, there's just one tiny little problem with the results so far. Because the experiment wasn't entirely fair yet, to be honest. That empty battery we've just punctured was completely drained. And draining a battery all the way to absolute zero causes irreversible damage, making the battery basically useless after that. So in reality, lithium-ion batteries like those in smartphones for example, never reach that point of absolute zero. There's always a little bit of energy that remains unused. And that's for a very good reason. Because that last bit of energy is what keeps the battery active and stable, making sure the next time you charge it, something like this doesn't happen. But it also means that even at 0%, there could still be a significant amount of energy inside that battery. And because we just found out that the amount of energy inside the battery determines how violent the failure becomes when it happens, I think the real question should be, how dangerous is a battery that's empty but not truly dead? Well, let's find out. I've discharged a battery all the way down to its lowest safe voltage, exactly where your device would read 0%. So technically empty, but not truly dead. Let's see what happens when we puncture this one. Ready? In 3, 2, 1. Well, way more explosive as our completely dead battery, but nowhere near as explosive as the fully charged battery. So yeah, the intensity of a battery failure depends heavily on the state of charge of the battery. But let's be honest, what are the chances of batteries getting punctured like this? In a real world scenario, it is unlikely for batteries to get drilled or stabbed like we just did. They're much more likely to be crushed or compressed in a real world accident. But how much crushing can they handle before something fails and things go south? That's exactly what we're going to find out with this next experiment. For test number 2, we're going to keep the battery intact. Well, basically, just no nail, no penetration. Just a slow, unstoppable force. But before we switch to the hydraulic press to really start crushing some batteries, I wanted to know how much of a beating these batteries can actually handle before something fails. And to do that, I put together this impact torture test rig to hit the battery with some hard, controlled mechanical impact. Again, controlled from a safe distance of course. Because now when I flip this switch, that small gear will start to turn, winding up the hammer and building up tension, until the last tooth slips. But before we start, how many of these hammer blows do you think it takes before the battery will start to fail? I'm guessing somewhere between 1 and 5. We'll get the answer right after this quick shout out to my fellow engineers over at PCBWay. If you are an engineer, an aspiring engineer, or just a hobbyist even, and you haven't checked out PCBWay.com, I think you should. Because I bet one of the services they're offering will perfectly fit your needs right now. Whether it's CNC machining, 3D printing, injection molding, or PCB design and fabrication, PCBWay delivers. Always. High quality, super fast, and best of all, it's way cheaper than you think. And I know because I'm a Dutch guy. So check them out over at PCBWay.com and tell them I said hi when you place your order, because who knows, maybe you'll get a discount, right? Okay, so back to torturing that battery and find out how many hammer blows will be too much for it to handle. Let's go. First hit. Okay, that's less damage than I thought it would be, but things can change quickly. Second hit. Still nothing. These things might be tougher to break than I thought. Third. Fourth. Fifth. Well, there goes my prediction. 6. 7. Even the thermal camera shows no sign of failure yet. But surely something is about to happen, right? 8. 9. So, number 10 should do it then. Okay, final blow. In 3, 2, 1. It actually seems like these things are designed to be able to take a hit. And when you think about it, it kind of makes sense. Because these batteries aren't just a thin, empty shell. Inside, these batteries are tightly packed with layer after layer of positive electrode after negative electrode. So instead of just a thin, empty shell, it behaves more like a solid tube which can absorb the impact much more easily. Okay, but if sudden force isn't enough, let's stop tapping the battery and start crushing it. Sudden impact might cause some hidden damage, but what happens when that pressure isn't just a sudden hit, but a slow, unstoppable force, like a garbage truck for example? To answer that question, I gave my old employer a call to ask if I could use their 50-ton hydraulic press to crush some batteries. Which is a weird question to ask, of course. But luckily it wasn't the weirdest idea they've heard come out of my mouth in the 10+ years I worked there. So it's time for some heavy machinery to simulate a real-world scenario. Exactly like something that happens far too often inside a garbage truck, for example. But what the heck happened inside that garbage truck, you might be wondering? Well, do you want to know why you should never throw your batteries in the trash? Here, I'll show you. Seems pretty clear to me, right? I don't think any further explanation is needed. And I know, so far we've taken things to the extreme, and you might be thinking, well, none of those things will ever happen to me, so why should I bother? Well, batteries can fail in a multitude of ways. Some are obvious, other less obvious, and some even invisible. And the thing is, it can happen at time you least expect it. But do you know what to do if you suddenly see a battery or a battery pack start smoking? What exactly should you do when you see a battery catching fire? That's what we're going to find out with the next experiment. Because there was a lot of debate around this topic in the comments. Some saying water can stop a battery fire without any problem. Others saying that water will only make it worse. So why not, instead of guessing, test both theories for real? To start, a fire always needs 3 elements to be able to start burning and maintain burning after that. Take one of them away and the fire will stop. Now, we're not going to take just one of those 3 elements away in a moment, but 2 of them, by submerging a flaming battery fully underwater. For this test, we're going to use the same guillotine setup we've used earlier, with a new fully charged 18650 lithium ion cell and a fresh and sharp steel nail. But this time I've added a little addition. Because this time, as soon as the nail has pierced the battery, a second servo will immediately swing the flaming battery down into a container filled with water. So if it's true that water truly cannot stop a lithium battery fire, then submerging it instantly should not solve the problem. But on the other hand, if just cooling the battery is enough to interrupt the reaction, it might stop it entirely. So, let's settle the debate once and for all. In 3, 2, 1. And for a moment it looks like it worked. But did it really? Because the flames don't even disappear. They seem to burn on top of the water somehow. And look at this scary sounding shot from underwater below the battery. Internal temperature of the battery remains extremely high, even underwater. Because once thermal runaway begins, the reaction doesn't depend on oxygen from the air. The battery generates its own heat and in many cases even its own oxygen, which means the fire and flames might eventually be suppressed, but the reaction itself inside the battery may still be active. So here's the real test. If thermal runaway is still ongoing, then the moment we lift it back in open air, the battery should start to heat up again. Let's find out. Well, there it is. Water can eventually suppress visible flames, but it doesn't instantly stop the internal reaction. To actually stop the battery from catching fire again as soon as you pull it out of the water is to cool the battery long enough to drop its core temperature below its critical threshold. And the bigger the battery, the longer that takes. That's why lithium battery fires are so difficult to deal with. Different scenarios with different triggers and different intensities, but the same fundamental truth. Lithium batteries aren't necessarily dangerous because they're unpredictable. They're dangerous because once their internal structure fails and a fire starts, the reaction can feed itself. So the battery becomes the fire.